Hello, everyone, and welcome to the webinar. Today's GETSI webinar is part of the NAGT webinar series. The NAGT webinar series is your one-stop shop for strengthening work in Earth education. Webinars in the series feature novel and innovative work in Earth education, research, and pedagogy, new teaching materials, and the classroom and professional experiences of people like you. The NAGT webinar series is free and open to the public, and we encourage you to invite your colleagues to attend and join the discussion. On the screen, there's a link to the webinar series where you can find the schedule, an archive of past events, and information on our sponsoring projects and programs. You can also find slides, resources, and recordings of each webinar, including today's, through the webinar archives. And I'll add some of those links into the chat here again. Next slide, please. Before we get started, please take a moment to review the Zoom controls on the screen. We ask that you leave your microphones muted and cameras off. If you have questions and comments along the way, and I can see that the chat is already cruising along, we encourage you to enter those into the chat box. To access the chat box, find the Zoom control bar and click on the chat button. Webinar presenters and staff will be monitoring the chat for your questions. Finally, a reminder that all participants in NAGT meetings and events are expected to abide by the NAGT Code of Conduct, which applies in all venues, events, and online forums associated with NAGT. Please read the full NAGT Code of Conduct policy, which I've linked to in the chat for any details. And with that, I'll turn things over to Beth, who will be introducing our topic and speaker.
Thank you. Welcome everybody to the Teaching Undergrads About Floods, Frequency, Modeling and Mitigation. This is a webinar about the Modeling Flood Hazards module, which is part of the GEodesy Tools for Societal Issues project. I'm Beth Pratt-Sitola. I work for UNAVCO, which runs the U.S. National Science Foundation's geodetic facility. I'll introduce the webinar, and then most of the webinar will be by Venkatesh Merwade from Purdue University, who was one of the two authors on the module and has been very active in hydrology education. To give you a little philosophical background, if you will, motivational background on why we have a project, called GEodesy Tools for Societal Issues. We know that there are a lot of societal challenges related to the earth sciences, be it from climate change, water resources, and natural hazards such as earthquakes or floods. We also know that we have a challenge of engaging students in STEM and making sure that we have a robust STEM workforce, science, technology, engineering, and math, as well as a literate, scientifically literate population. So it turns out that there is a complementary path to improvement with these two challenges, because if you feature the science and technology and engineering and math learning in the context of the societal challenges that we can address, students not only learn it better, but they're actually more likely to be engaged in science in the long term and be more science literate in the future. The GETSI project has the mission to develop and disseminate teaching and learning materials that feature geodesy data and especially quantitative skills applied to these critical issues that geodesy can help us with, which is climate change, water resources, and natural hazards. It is a sister project of a larger project called Integrate, which is also looking at teaching earth science for a sustainable future. We've had 4 grants so far from the National Science Foundation of the US, developing a total 13 modules that are something like 2 weeks or so each, depending on how you teach them, both introductory and majors level, as well as classroom and field. Today, it's a majors level classroom module. Just to make sure that we're all on the same page about what I mean when I say geodesy, it is the science of accurately measuring the Earth's size, shape, orientation, the mass, where it is, and how it's moving around with time. Traditionally, or originally, we could say it was really just precise positioning of points on the surface of the Earth. I mean, when we really got going with surveying, it was just hard enough to know how far, say, Berlin and Paris were away from each other. But in the last few decades, we've really emerged a toolbox of techniques to better measure the Earth. And if you go to unpack this geodesy toolbox, it has a global positioning system, or more the global navigation satellite system, GNSS. There's radar, usually satellite-based radar, SAR. High resolution topography, be it from LiDAR or structure from motion photogrammetry, is also considered to be geodesy, and that really is the primary data source in the module that you're here about today, is this high resolution topography that really lets us do a better job with the flood modeling. Strain meters, tilt meters, creep meters, gravity measurements, especially the GRACE gravity satellites, and sea level and ice altimetry. So that's the larger toolbox, although today most of the data is coming either from LiDAR and with some GPS components as well. Behind each of the modules in this collection, and the one you'll hear about today, there are 5 guiding principles. And so one is to address geodesy-related grand challenges facing society, make use of authentic and credible geodesy data, improve students' understanding and the ability to communicate and, sort of partake in the nature and methods of geoscience, develop student ability to address interdisciplinary problems and apply these to geoscience learning of social issues. I really, think this is where the societal issues part of it comes in. So students need to move beyond just understanding that floods can impact society, for example, but really, being able to say more about what aspects, along a river might be most threatened and what would be some mitigation options. And to increase student capacity to apply quantitative skills. The modules are all developed using what's called a backwards design method. This particular program was developed, an assessment model was developed by the Integrate project. It uses backwards design, which means you start with the learning goals and then the more sort of granular learning outcomes. The next thing to do once you know where you want your students to get is to determine the assessment strategy of how you would know if they got there. And only then do you move on to designing the actual teaching materials and the instructional strategies. All of the materials are piloted by our authors and a non-author pilot tester. They're revised and then published. So before I hand it over to Venkatesh, I'd just like to make the suggestion that you take some notes for yourself about aspects of the module that you are most interested in, or steps you would need to take to integrate it into your own teaching. So if you come back to this, in December or January when you're putting your next syllabus together, it will be more helpful for you if you've left yourself some notes on how you'd move forward. So with that, I'm going to stop sharing and Venkatesh will take over. Take it away.
Can you see my screen?
Yes. It's not yet in presenter mode.
Are we good?
There we go. Yep.
Okay, thank you, Beth, for the introduction. I want to thank everyone who is attending the webinar. So I see people from all over the world. So we really appreciate your time and interest in what we are presenting today. So before we get started, I just wanted to get a sense of who you are. So we are just going to do a short poll and just tell us about yourself.
I think we'll go ahead and end the poll and share the results.
So I see many of you are teachers, so about 40% of participants are teacher, and then the next group is students, so which is good. So this is the audience we wanted to reach, so that's good to know. Many of you or some of you showed interest in actually learning about modeling and all that when you answered the questions during registration. So I just wanted to let you know that we have 1 hour. So there is a lot of material to cover. So my goal here is to give you a flavor and some idea of what the module is about and get you excited. And hopefully you will get excited, and then you will use the links and all the resources that we provide to implement the module and maybe learn what's involved in some of the exercises. So this is a teaching module to teach about flooding, how to estimate flood magnitude, how to simulate floods, and discuss mitigation strategies. It is divided into 5 units, so we can think of 1 unit as a lesson. So depending on how you want to implement it, you can actually finish this module in 2 to 6 weeks. So 6 weeks meaning you go 1 unit every week and you finish 5 units, and then there is a project towards the end. If you want to skip some units, you can finish it sooner. So that's why I gave you a range of 2 to 6 units. So the audience for this module is mostly advanced geoscience, earth science, civil engineering, and environmental engineering students. And the field of geoscience and earth science is very broad. So you can think of hydrology, geomorphology, geostatistics, and so on. There is a link provided to the module here on this slide. So I don't want you to click at that link and start exploring at this point. You will get access to the PowerPoint and the webinar later, and you will have plenty of time to explore what's available on the module site. So there are 4 module goals, and to the left, you will see a description. So we want students to be able to describe flooding and its role as a natural process versus hazard. We want them to learn some concepts, and I'm in an engineering department, so we went through the probability route. So many times we have limited data on flooding and stream flows. So how can we use probability to estimate flood magnitude for a given return period? Now, some of you may know what return period is, some of you may not, and that's again something that is included in the module. And the third goal was to, once you have the flow, you create the flood inundation map, and then you translate that flood inundation into societal risk and propose some mitigation strategies. So that's the sort of conceptual thinking behind this. And to the right, if you see those 4 boxes, so that's how basically the procedure of flood modeling and flood mitigation goes. So first you want to understand about the flooding situation, and then you want to solve that problem. And in order to solve the problem, you need data. So you need to know where the data comes from, how to analyze that data. It involves some modeling, hydrologic and hydraulic modeling. You do that, and then you create a flood inundation map. So besides the teaching part and the theoretical part, we also wanted the students to have the skills that they can use to in real life scenarios, and if they start working in this profession, they should be able to use all the skills they have learned in this module. Again, at the bottom of this slide, you will see the link to the module. So that is for you to check it out later. As I mentioned earlier, there are 5 units. So unit 1 is Introduction to Flooding. Unit 2 is Flood Frequency Analysis. Unit 3 is about studying channel capacity, and more specifically using of Manning's equation to estimate water depth and width for a given flow. And unit 4 is the hydraulic modeling part using HEC-RAS. And unit 5 is a sort of a summative assessment, or where the students work on their own to apply skills that they have learned in unit 1 through 4. And what I plan to do in this webinar is briefly go over units 1, 2, and 3, and spend relatively more time on unit 4, and conclude with brief discussion of unit 5. And throughout this webinar, we are going to pause and ask you questions, and also give you opportunity to ask me questions or Beth questions. Okay. So again, here comes our next poll. I'm curious to know what operating systems you use or you're familiar with. So we have Windows, Mac, or both. So most of our audience is Windows user, so that's me too. So 68% of audience say they use Windows only, 13% says Mac only, and 19% they can use either. So that's good, because the next slide talks about the technology requirement for this module. So Windows operating system is preferable because the main modeling piece that we use is HEC-RAS, which is Windows based. You can use it in a Mac machine, but it is a little tedious, especially for students if they are not familiar with that. We also use ArcMap in some of the units, and this is mostly used for displays. So if you or your students are familiar with ArcMap, that's good. If not, they should also be able to finish that task using Google Earth or QGIS. So you really don't need an ArcMap license, because I know many universities don't have that, especially in countries other than US and maybe Europe. Some of the exercises involve Microsoft Excel, but again, if you don't have Microsoft Office, any spreadsheet program should work. And finally, the HEC-RAS version that we use is 5.0.3 or higher. The main reason for that is it has RAS mapper, which is you can think of as a GIS inside HEC-RAS, and I will go into more details of that later. And HEC-RAS is mainly Windows based, so that's why if you are a Windows user, it's much easier to finish this module without any technical difficulties. But as I said, even if you're using Mac, there are ways to install HEC-RAS. So let's start with Unit 1. So when I start Unit 1, the main goal of Unit 1 is to get student not just excited, but also understand the context of what flooding is, why do we need to study flood, and how we can do something to mitigate the risk and reduce flooding. So usually I start Unit 1 by asking these questions to students, and then there is a discussion around those students. But right now we don't have time for that, so maybe we can just do the poll and see if any of these three apply to you. So the poll shows that about 70% of our audience or someone they know has been impacted by a flood in recent past. And that's true for me too. I live in Indiana that gets flooded very often. The Midwest of the US gets flooded very often. And just in the last few days, we had Hurricane Sally, not in Indiana, but in the coastal region of US. So many parts of US get impacted by flood. Originally, I'm from India. My family home in Kolhapur was flooded last year. It was under 6 feet of water. So many of us are impacted by floods. So that's why we see the importance of mitigation. So the next question was, are all floods bad for us? Some of you, 24% said yes, and 76% surprisingly said no. And it depends. So depending on how big or small the flood is, the small floods can be good for us in terms for the ecosystem especially. And the last question was, 100-year flood will not happen again in the next 100 years, and 12% of you said that is true, and actually that is not true. And that is something that we also teach students in this module. So let me go to the next slide. So this is basically sort of module 1. This just gives you an overview of flavor of what is contained in unit 1. So we start with the definition of floodplain. So how do you define floodplain? When the water flows over banks. So that's the natural way of defining floodplain. There are different types of floodings. As I mentioned, from hurricanes and storm surges, we get coastal flooding. When we have a lot of rainfall, we get riverine flooding, and many times when we have thunderstorms, we get shallow. And when our urban infrastructure get flooded and the water has nowhere to go, we also get a lot of flooding in urban areas. We discuss the role of humans in flooding. So on the right, you see an image on the bottom where when you modify the floodplain, you increase the risk of flooding. So we discuss topics such as how watershed development impacts the occurrence of flood, how development in the floodplain affect the occurrence of floods, and so on. So we discuss that. Then we discuss what kind of management strategies are available for floodplain management. So we talk about structural measures and non-structural measures. So structural measure meaning building of dams, building of levees to stop water, and non-structural measures will include things you can do at the watershed scale or in the floodplain for that water to flow somewhere else and not flood. Then we talk about floodplain management strategies. And many of these topics and the discussion that we use, it comes from FEMA documents. So we use that, the reason being that, again, this is for the students in the US. If they end up working in this profession, many of these flood projects are managed by FEMA. So that is a way for us to introduce them to the right terminology and resources that they can use when they work in this area. And finally, we end unit 1 in going into the hydrology of flooding, what hydrographs are, what return period is, what exceedance probability is. So the discussion of return period again starts with a question that I asked you in the previous poll. Will a 100-year flood occur again in the next 100 years? And many students who have not heard this term, they say, oh, if we got the flood this year, it should not happen for another 100 years. And that is not true. So we go into detail of how return period is defined. And then we do an exercise on how you can calculate flood frequency or return period for a given set of data. So we give them a long data set, at least 100-year long, so they can get the return period for 100-year flow. And then we have them comment on what they find. So there are two aspects of what student will do in unit 1. One is about quantitative. So quantitative meaning they work with the data, and we give them one data set for urban area, one data set for rural area. That way they can see how the 100-year is different for an urban area compared to rural area. And then we have them comment on why the difference is. That's the quantitative part. And then there is a qualitative part. So qualitative part involves students going and find resources that are available on flood information. So what you see here is the it's an interface from NOAA, Advanced Hydrologic Prediction System. So there are about 7,000 USGS. So USGS stands for United States Geological Survey. They do all the stream monitoring. So at all these gauges, the National Weather Service can do predictions, and they have this system where they have defined what an action stage is. So depending on the level of water in the stream, if the water goes above that yellow line, then it's an action stage that we then above that there is the minor flooding, major flooding, and depending on where that water level is, there are different actions that the agencies can take. So what we do in qualitative part is we give students different areas or counties, and for each county we have them go and find this information. So what I'm showing you here is for an area in Michigan. So after they look at that interface, we have them go get the data for a nearest gauge and see how many times in the past 5 to 6 years the water level has exceeded the different stages that are defined by the National Weather Service. We also have them get the 100-year floodplain map from FEMA and map that using either ArcMap or QGIS or Google Earth. So they get a sense of how much area is within that 100-year floodplain zone. And then we have them do more research on how often that area got flooded in the recent past, what happened, and what infrastructure changes or strategies that the city or the town has taken to handle some of these flooding events. So this is how Unit 1 ends, students getting a brief overview of what flooding is, and then they're doing some quantitative and qualitative work. And with that, I will just pause to see if you have any questions on Unit 1. Let me see if I can see any. So
Nothing has come in yet.
okay.
There was a question, let's see, I used this exercise in my geologic hazards class and noticed that the USGS gauging station names and numbers are not given the same name and number on the National Weather Service advanced. So that's Susan, she actually tested this for us. More of a statement than a question.
Okay, so that's something we can also make a note in the module. So
yeah, I'll add that.
They can be sure. When I have used it, I usually go to the USGS site, and for each gauge there is a link to go to the NOAA site. So that's how I go there. But again, this is something we can incorporate. So thank you, Susan, for that comment. So the next unit involves, so let's say we are interested in flood now. The question is, how do we get the flow magnitude? How do we get the flood magnitude? So the two questions that we are trying, or we want students to answer from Unit 2 is, what is the likelihood that a flow rate of a certain magnitude will occur in any given year? And how often will a flood of a certain magnitude occur? So this is the classic flood frequency analysis topic in hydrology. So we try to cover that in Unit 2. And in my class, I have done this with fourth-year students. So some of them, or many of them, have taken some statistics class before coming to my class. And depending on whether you want to teach this to third-year students or fourth-year students, some of them may not have background that you need to finish this unit. So my colleagues, when they implemented this unit, they had their students go to this COMET tutorial. This is again from the University Council for Atmospheric Research, UCAR, and it's free resource. So you can have your students do this tutorial before you start with Unit 2. So one of the things that we emphasize in flood frequency analysis is that the data that we have, in order to compute these 100-year design flow or 500-year flow design flow. We don't have enough data. So we show them the disadvantage of using a sample data set. So again, the PowerPoint that comes with this unit goes into the basic probability and the difference between sample data and population and all that. So that is all covered. So here we show them what happens when you compute return period or flood frequency using a limited data set. So what they see from this exercise is that the data is coming from the same population, but depending on the sample size, you get different results. And that's how we introduce them this concept of sample data set versus population and so on. So we cover the probability concepts, and the other key concept that we also cover in this is the difference between discrete probability and continuous probability. So in discrete probability, you look at probability of something happening for a given value, but in flood frequency analysis or the stream flow, you are never certain that you are going to get this particular value at any given instance. So instead, we use this continuous probability or exceedance probability. Then we have them understand what annual maximum series is. So instead of using the whole data set, we use annual maximum series. So annual maximum series is just one of the time series you can use. There is partial duration series and other types of series which are included in the PowerPoint. Then we have them go through the probability fitting exercise. So there are different types of probability distributions. Which one you use? Do you use a normal distribution or you use a skewed distribution? So in this case, you see a normal distribution, but eventually we have them compute return periods and flood frequencies using skewed distribution. So in this, you see extreme value 1 distribution, and we also cover log Pearson type 3 distribution. And then we have them pick a data set and fit a distribution and calculate design flow and for a given return period. So here you see they plotting a histogram and then fitting a distribution and then calculating flow for different return periods. So, and then at the end, they turn in a flood frequency plot. So when they finish Unit 2, students know how they can calculate flow for a given return period or how to get a design flow. Once you have the design flow, then you know how much water is going to flow through a river or a stream. And then we can start thinking about what the impact of that flow is. So Unit 2 is about getting the design flow that you are interested in. So with that, again, I'll pause for Unit 2 to see if somebody has any questions or comments. And Beth, I'm going to have you do this when I push out it.
Sure. So there's been a variety of things that people have commented on, and we've been trying to answer in real time. For instance, that this module has been successfully used in a hydrology course, a geomorphology course, geohazard courses. It's really designed to hopefully be able to work in a variety of different places. People also pointed out that the data sets that are specifically within the module are US based, and we acknowledge that it is US funded. And so if people know sort of a comprehensive set of the equivalent data for other locations, I'm happy to put those into the notes down at the bottom of a given unit. And Charlie from Canada put in one already. So let's see, one question. Do you recommend statistics be a prereq, or is it enough to cover the fundamentals in these units?
A prereq would be ideal, but I can see how that can discourage many students. So as I mentioned, the COMET tutorial from UCAR does cover some, and the PowerPoint slides we have, it does cover, again, it doesn't go into all the details, but it gives them a flavor of what statistics is and why it is important in doing flood frequency analysis. So
One question about the Comet tutorials. I believe they're free. I know I've taken one and I'm pretty sure I don't have to pay for it.
yes,
They're
they
free,
are
right?
free. You
Mhm.
may have to get a login, and which is not a difficult process. So it doesn't matter whether you are in US or outside US, you should be able to get a login. And there are lots of many good tutorials there. Yeah.
And Susan did mention that she simplified the flood frequency analysis so it didn't have advanced statistics. I think it's definitely, you can go farther or less far with the statistics depending on your particular student
Yeah.
group. What role satellites data plays in the flood mapping assessment?
Um, we can get to that question maybe towards the end after we do the
Okay,
inundation mapping.
sounds good.
So you need to ends with getting the flow magnitude. So we are interested in flooding, which is the water depth and extent. Then, so what we want students to learn in unit 3 is, okay, how does flow gets converted into a depth and the width? And that is the essence of unit 3. So for a given flow, what will be the depth, velocity, and top width of water in the channel? So this is the unit where we go into the geodesy part. So in order to do that, you need to know the shape of the river, the topography around the river, and we go into brief presentation of what geodesy is, what techniques are available. So what you see on this slide is a survey being done on a boat. There is an echo sounder there. That echo sounder sends signal into the riverbed and calculates the water depth. There is a GPS antenna that gets the XY location for all the points where the water depth is being measured. And depending on the equipment that is used, you end up with different data sets. So on the bottom, you will see a data set collected using a multi-beam echo sounder. So multi-beam, you can see there are millions of points. With single beam, it basically 1 point per second, or how fast or how slow your boat is moving. It basically captures the path followed by the boat. With multi-beam, it just collects the entire swath of the cross section. So depending on which equipment you use, you end up with these points, and eventually you can use interpolation techniques or any other techniques to convert that information into a river bathymetric surface, and that gives you how the river shape is. And then we go into basic physics of flowing channels just to get them introduced to the Manning's equation. So again, it's a basically um, uh, a conservation of mass, energy, and momentum problem. So water flows down here and it's flowing under the force of gravity. Then the channel is resisting that flow, and then all these forces are balanced, and that analysis yields to this Manning's equation. So we sort of derive this expression, and then we have students understand what each term means. So the Q is the discharge, and A is the cross-sectional area, S is the slope, and R is the hydraulic radius. And then there is this Manning's coefficient, which basically is the roughness coefficient. So depending on the value of N, the flow will face less or more resistance. So if the N is smaller, there is less resistance. If N is higher, there is more resistance to flow. So once they have this equation, we have them do an exercise. So we give them a cross section, and we have them calculate the perimeter and area for a given flow, or and then we have them estimate velocity and other variables that are involved in the Manning's equation. Basically, we have them calculate the cross-sectional area and perimeter using an Excel sheet, and this Excel sheet is provided to them. So there is one problem already solved, so they follow that and they do it for another cross-section. So you see one cross-section here, and the other cross-section that is not captured on the screen is in the green color there. So, and I don't know if you can read the table 3. So table 3 is where all the values are calculated. So this is a sort of pre-programmed Excel sheet. The idea here is for them to get the area and perimeter for an irregularly shaped cross section, instead of, in most of the times in textbook they will be dealing with trapezoidal channel or triangular channel, but here they deal with the actual survey data to get the information they need to apply the Manning's equation. So this is what the students do. They start with the flow and they end up with the area and the velocity corresponding to that flow. And this is the time to ask if you have any questions for Unit 3. If not, let's move to Unit 4. So from Unit 3, they understand.
Oh, there's a question. Can you please share this Excel program with equations? So all of the spreadsheets and stuff that we show here are, in the online free open module that that you can explore.
Yes. So the link was provided at the beginning of the webinar in the chat box. It's also in some of my initial slides. So after the webinar, you will get access to the webinar video and also this PowerPoint. So you can explore all that information once you get that link. And if we get time at the end, we can again post that link in the chat box, or I can go to that slide. Okay, so let me go to the next slide. So in Unit 3, so from Unit 1, Unit 2, Unit 3, students know how to get the flow. They know for a given flow, how that flow gets translated into water depth and velocity and so on. So they do that for one cross section. So the idea of Unit 4 is to do that for all cross sections or for a long ridge, and it's not easy to do that manually, and that's why we introduced them HEC-RAS model, a one-dimensional HEC-RAS model. And we tell them that what they have done for one cross section is sort of done for all the cross sections, and we go into some equations of HEC-RAS, and depending on how familiar you are with HEC-RAS, you can go deep into those equations. If not, you can just wave your hand and show them what is happening and how Manning's N is used. So they use HEC-RAS, and then one of the exercise we have them do is the effect of overbank roughness. So as I mentioned, the roughness is the Manning's N coefficient, and one of the things that they learn in Unit 1 is the impact of human development in floodplain. One way to think of that is increasing the roughness in the floodplain. So we have them play with the roughness value to see how inundation changes depending on how high or low the roughness value is in floodplain. We have them create inundation maps, which are basically GIS files, which they can use to overlay with other infrastructure data to look at what damage it will cause, and then think about this societal decision related to flood zone management. So again, a poll question here, just to see how many of you are HEC-RAS users or have used it before, never used it, not interested at all. Okay, so some of you have used, so 29% said they have used it, 16% said they tried but not successful. But majority of you have never used it, but you really want to use it, which is good. And we have good resources for you to get started. And also for those of you who were not successful, so hopefully the resources that I share you in the next slide will be useful. And 9% of you said you are not interested in using it, so which is fine. So let's go to the next slide. So HEC-RAS is free. As I said, it is Windows based. So the link to download the software is given to you on this slide. When I was working on this slide, I also saw that they now have a Linux version. So if you're not a Windows person, if you're a Linux person, you should still be able to use it. There is a lot of learning material that I have created for HEC-RAS. So if you have never used it, these basic introduction to HEC-RAS links that I show you here will be very useful. The first link is a PDF file, it's a tutorial. The next two links are basically YouTube videos that you can watch and follow along. And once you do the basic introduction, you can do the last one, which is creating a HEC-RAS model for a river reach. And this is the same exercise that the students will also do in my class. So these are very useful resources. So those of you, the 50% audience who said they are really interested, this is a good place to start. And hopefully by the end of doing this tutorial, you will feel confident with the software. So I will just share some slides that we use in the presentation part of this unit. So as I mentioned, we use one-dimensional HEC-RAS model. You can also do two-dimensional modeling in HEC-RAS. So we just go through different types of model, why they are used, why do you want to use 1D or versus 2D or 3D and so on. So we give them an overview of different types of models, and then we spend some time talking just about HEC-RAS. So what you see on this slide is a HEC-RAS geometry file. So there are a couple of things that you need to have before you can set up a HEC-RAS model. And I will go through that in the next slide. So you can run it either in steady state or unsteady state. So again, those of you who are not familiar with it, the PowerPoint goes into what is a steady state, what is non-state, unsteady state. And we use one-dimensional model when we are mostly interested in the flow that is going to go in one direction. And that is typically the case when you have very high flow. If you are thinking about 100-year and 500-year flood, that is that mostly goes along the channel direction. So as long as there are no split flows or branches, then one dimension is a good assumption to use. So I'm not going to go through all this. We don't have time. So again, the idea here is to just show them how the energy equation. So in my class, it's an engineering class. So many of the students take the basic fluid mechanics or hydraulics class, and they are familiar with the energy equation that you see here at the bottom. So the basic idea behind a one-dimensional steady-state HEC-RAS model is solving this energy equation and the head loss. And the head loss term involves use of Manning's equation. So Manning's equation here is applied in the main channel, in the left bank, in the right bank separately, because the roughness values are different. And this is where we show them the link between the Manning's equation that they have used in Unit 3 and how it is being used in HEC-RAS to do the calculations for all the cross sections for a given reach. And then this is just a summary of how the program solves the flow depth and velocity at each cross section. So it's a trial and error method of solving the energy equation. It's called step method. So those of you who are familiar with the open channel flow equations. Yeah. So as I mentioned earlier, you need to have some data in order to set up a HEC-RAS model. So you need to know the river channel description, how long the reach is, what is the slope of the reach, what's the roughness values are in the channel and in the floodplain, and then you need to know the cross-section geometry. And that cross-section geometry comes from topography data. And then you need to have some boundary conditions, and these are mainly what the flow of water is on the upstream end, and if there is any downstream control, and then if you have any river or river structures such as bridge, culvert, weir, levees, you need to have information about that too. In the simplest case, you can exclude the structure geometry, and if you just have the channel geometry or the cross-section geometry and boundary condition, you should be able to set up a HEC-RAS model. And in the links I showed you earlier, the basic introduction to HEC-RAS basically does just that. So those of you who have not used HEC-RAS, this is how the program looks. So initially, when you open it, you will not see all these names. So when we do unit 4, we actually don't have students create the HEC-RAS model. We give them a ready-made HEC-RAS model, and we explain them what's already included, and we have them input only the flow information, run the model, and spend time looking at the results. So when a student starts this unit, this is what they will do. They will open the model that is given to them. And this is the RAS mapper. So in the beginning, I said you need HEC-RAS version 5.0.3. And the reason for that is it has its own built-in GIS program. So when you open it, you will see the topography, and you use that topography to draw these cross sections. And then for all the lines that you draw, the elevation gets extracted from the underlying topography. So if you select a line and say, okay, show me the cross section, it will show you the cross section. And the black points that you see here on the cross section are the elevation that are extracted from the topography that is provided in the RAS mapper. So this is all given to the students in the model that we give for Wabash. There is also a bridge, and if you click on that bridge, it will show you how the bridge will look like. And then as I mentioned, most of the information they need is given to them. All they have to do is run the model for different flows. So in this case, we give them the flow for Wabash for different return periods, and we have them run the model, create inundation maps corresponding to this return period, so they can see how the flood inundation changes when the design flow changes. So we are running out of time, so I will run quickly through this. So you provide the information. There is a tutorial that goes with this, and the tutorial has all the detailed information on what the student has to do, and it's very easy to follow. And if you follow the tutorial, you run the model, and after you run the model, it will give you the water depth and velocity for each cross section. So this is just a cross-sectional view of what the water depth is at this particular location. You can look it for the entire reach, or you can look it in 3D on how the water surface would look like. Finally, we are interested in the inundation map. So they can go back to RAS mapper and see how much of that area is inundated. Now you can see that this doesn't show you what else is being flooded here. It's just a topography data set. So we have the students export this into a GIS shapefile, and then they can plot that shapefile or a KML file into Google Earth or QGIS and see if there are any schools that are getting flooded, or are there any hospitals, or is there any other infrastructure that gets flooded. and based on that, they can see how the flood is impacting the surrounding areas. And finally, in Unit 5, what we do is we give them study areas. We have them pick one of the study areas, and we basically have them do Unit 2 and 4 on their own, and then write a report. So these are the data sets that we have for Unit 5, and everything is pre-packaged and ready to go, so students have all the information they need. So the idea here is that they go and they do everything that they have learned on their own, and they write a report on what the flood impact is in that particular area, and we have them propose mitigation strategies based on what they have learned in Unit 1. So I think,
and just to jump in, we now have a Texas and an Idaho river in addition to the Indiana ones that he showed in the last slide.
yeah, so this is just my final slide. As Beth mentioned earlier, we have implemented these lessons at Purdue. That's me and my colleague Jim McNamara, who is the co-author of this module. He's at Boise State University and UC Santa Cruz. And some of the lessons or challenges, so timing and sequence is the key. So if you try to do this towards the end of the semester, it becomes sort of difficult. So it's good to plan ahead and make sure that the topics that you are covering align with what's in these units. And as some of you mentioned earlier, some of the math can be overwhelming. So depending on your audience, you can modify some of these units. And obviously there are some technology barriers, especially if you are not a Windows user. If you have not used HEC-RAS, there is a learning curve involved, but it is not very steep. It's an easy model to learn. So with that, I stop. I think we had some questions along the way, and I don't know how much, so we have maybe 3 or 4 minutes for more questions. There is contact information here about me. If you have any questions, you can contact me. If you want to use the module, if you want to get in touch with Beth to implement this, I think there are some resources available, if I'm not mistaken, Beth. So with that, I will stop here. And thank you very much for everyone who participated.
Thanks so much for everyone. We are just near the end, so I think we may only be able to get one more question in before we have to close, or two. One question, in case we don't have lighter or high resolution data, is 30-meter data okay? And really, I think the answer is no for that. You really need to have some more nuanced understanding of the topography in the river channel.
So maybe I can just add to that. It depends on how big or small your river is. In some cases, you could get by if your flow is very high. And again, if your idea or goal of teaching is to give them the skills, it should be fine, but they may not get the actual understanding of how that flow is affecting that particular area. So there are pros and cons, but if you don't have anything else, you could basically do Unit 4 using a 30-meter DEM. But I would pick a larger river that is much wider, and the floodplain.
For that kind of data. Well, thank you so much, Venkatesh. I think if you don't mind advancing to the last slide, Mitchell will close us out. Thank you, everybody, for your really interactive attendance today.
So again, thank you, Venkatesh, and also thank you, Beth, and thank you, everyone, for joining us. The next webinar we have in the series is Navigating Life as a GER student. That's Geoscience Education Research student. That's Wednesday, October 7th at 7 p.m. Eastern Time. We invite you to join us and register using that link. As always, we invite you to please take a moment to fill out our webinar evaluation survey. I've put a link to that into the chat box. If you have a few extra minutes, we would really appreciate your feedback. And with that, thank you again for attending, and we hope to see you at a future webinar.